Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Kyle Augustson with us today. Oops, blew that one. Hey, Kyle.
Hey, how's it going, Frank?
Good. Where are you located at?
I'm currently staying in Salt Lake, waiting to move to Chicago after moving here from France a couple of months ago. Yeah, still waiting on my stuff to arrive. It's been about 3 months, and
Okay.
here in a couple of weeks, I hope.
Is it coming over on a ship or on an airplane?
Yeah, I did the slow route.
Okay. Well, it's okay then. It's all good. So you're taking up a new position in Chicago, or?
Yeah, Northwestern. I started back in March, so I'm kind of working on some new projects related to that, but a little different than what we'll be talking about. But that's just fine.
Okay. Very cool. Very cool. How is summer in Utah?
Well, like a lot of the West, it's been pretty baked. It's a little cooler than it has been the last couple of weeks. It's somewhere in the 90s Fahrenheit, about 36 Celsius, I think, something like that right now.
Pretty toasty
heat
for,
of the day.
Parts of Utah. Absolutely.
Yeah. Just went on a nice little barefoot walk around the neighborhood and got my toes scorched a little.
There we go. Yeah, we're a little cool today, July 2nd in Phoenix. We're at about 105, so 35, 36 C or so. Yeah, so all good. It's a good summer so far.
Awesome. Despite the 115 degrees that you guys had last week or the week before, something like that.
I actually like it. To me, it's perfectly fine. Yeah. So Kyle, what do you like to do for research?
So I'm kind of all over the place. I do a bit of numerics, so building algorithms to do 3D simulations of convection and magnetism. I've been doing some analytical work in more recent years, which we'll be talking about today. I'm currently doing another amalgam of linear analysis and then doing some nonlinear problems associated with it. So basically, it's linear and nonlinear analysis is my kind of forte.
Awesome. Very nice. And that is going to bring us to this very lovely APJ article, a model of rotating convection in stellar and planetary interiors to gravito-inertial wave generation. And Kyle, take us away.
Sure. Okay. So this is the second of two papers. We may have a third coming out eventually.
Great.
But basically, we wanted to take a pretty simple model of convection. In this case, looking at something called Rayleigh-Bernard convection. So really one of the simplest setups you can have, where you just have a hot plate and a cold plate with some gravity. And what we do is we introduce rotation into this picture and try to derive a mixing length-like theory that includes some of the effects of rotation.
Okay.
And paper one basically looked at how this can influence convective penetration using a model developed by Jean-Paul Zahn in 1991, which is basically you linearize the system near the interface of a convective region and a convectively stable region, like say near the tachocline of the sun or near the top of a core in a massive star, and looked to see how that would impact mixing coefficients that are commonly used in stellar models. Basically there, we just found that the diffusion decreases significantly the faster you rotate, to the point where you basically almost have no mixing, giving classical models anyway, for fast rotation. Okay. Then the next idea was to say, okay, well, we know that this convection is going to excite waves at this interface, specifically gravity waves. And then when you add rotation in, you also throw in inertial waves, so these Gravito-inertial waves that are generated by convection as well as interfacial deformation. And we'll get to what I mean about that in just a little bit. Okay. But basically, we just take this model and apply a very simple linear model of waves that has two regions. So if we go look at figure one, we can take a little peek at that.
Look at figure one here. There.
Yeah. So basically, the idea here is.
Sorry about that, people.
No worries. Jumped around on us.
Okay, there we go.
All right, so figure one kind of shows how this system is configured. So basically on the right, or on the left there, you see the sphere, which is trying to represent our star. In this case, it's basically a sun-like star where you have a convective outer layer and a stable inner region, but there's no reason that you can't just switch the geometry around because it's a completely symmetric system to have something that's more akin to a massive star core and then a stable region above it. Because this is Boussonesque, basically Boussonesque Rayleigh-Bernard convection, you have no stratification, so you don't have to worry about the direction of the density gradient in this case.
Okay.
Density is constant. So basically, we take a little piece of that, and we want to say, okay, we have nice Cartesian geometry where we can do the linear problem very simply, and we want to look at how waves propagate in that yellow region down below there. So in the orange region is your excitation region where you have all your convection that's driving the waves both at the interface and through kind of the evanescent tail of the waves that is also present in the convection zone.
Okay. And
one reason that we want to get into this is that we have observations coming out now with sufficiently long time with Kepler, this 4-year kind of data of Kepler, that you can start to pick out these modes with sufficient resolution that you can really do mode detection well for massive stars in particular. Really looking at stars more massive than F-type stars where you can see Gravito-inertial modes more easily. For instance, in the sun, the amplitude, the predicted amplitude of the gravity waves is quite low relative to the sound waves, something like 10 to the minus 7 in the amplitude of the sound waves. So very difficult to detect, although there's been some papers that have claimed some detection of gravity, of very low order gravity waves.
Yes.
And the reason this is of interest is that these modes dive deep into the star, and you can sample the interior of the star and get an idea of what maybe magnetic structures you have there, what the flow structures look like, and even just what does the stellar structure look like? What is the interface between, say, convective core and its surrounding stable region look like in terms of what are its mixing characteristics, etc. So this is kind of a preliminary look to get an idea of what mode amplitudes you might expect for those kinds of Gravito-inertial waves or gravity modes. And so this is building on much earlier work starting for the convection model back in the 1950s with work by Malkus and Howard. So Malkus 1954 and Howard 1963, which kind of provide a framework to build a convection model that's quite simple, but one that has some rigor behind it. Particularly looking at the power integrals that are developed in Howard. And there's basically one principle that Malkus developed that drove a lot of kind of modeling of convection and analytical work in convection following that. And that was basically the convective flux maximization principle, wherein that you have a convective system, it has some dissipation, thermal dissipation in this case. And you look at something called the Nusselt number, which is basically the ratio of how much convective flux you have to diffusive flux. That tells you how efficient the convection is in your system. And this provides a way of getting at that number and kind of describing the convection in an analytical way with a relatively simple model, which we use here to describe our convection. And it looks like my camera froze again.
Yeah, you're temporarily frozen here.
Yep, let me restart that camera again.
All good.
If it's coming up, stop video, start video.
All
right, there we are again. We'll have to do that periodically, I think every 5 minutes or so. Sorry about that. Yeah, so that's the basis of kind of the convection model. And then, like I mentioned, we have these observations that are kind of driving this work in the first place, trying to find a way of describing how much flux you should expect, what modes you might expect. And we have some additional work on this that we've done, and some not AppJ articles, but some ANA articles regarding the spherical version of this, where you, instead of having a purely kind of analytical convection model, you use a statistical convection model, which is much more widely applied throughout stellar physics.
Okay.
Anyway, okay, so this is our geometry. You've seen that. So the first piece we need to get this moving is to look at the model of convection itself. So if we look at just the first equations, go down a little bit further to Rayleigh-Bernard convection. Okay, so yeah, what we're seeing here is the result of linearizing the convective system, so in that domain that we had, where you have rotation, you have buoyancy, and some diffusion. Yeah. So you have both diffusion of the thermal structures as well as the velocity structures. So that's described by nu, and the other is described by kappa. So this is one change to the models that we have been using, is to add diffusion into these. We don't really use that explicitly here, but it is available as an option to explore how that can impact your convective structures. But generally, most stars are highly nonlinear and have very large Reynolds numbers, so the diffusions are quite low. So here, those are basically neglected, but it is there as an option to look at.
Okay.
And what we want to look at is two things. So this gives us our linearized system, and this tells us how the growth rate of those convective modes is related to its wave number, which is influenced by both the diffusion as well as the rotation. And so if we scroll down a little bit more, there's another principle that we have to enact. And it's the heat flux maximization principle, which you can see there in equation 11 and equation 12. So this tells you how the kinetic energy, or the convective flux, varies with the growth rate and other parameters of the system. And what we want to do is maximize this function with respect to wave number.
Okay.
It gives us an equation for that wave number that describes the basic mode of the convection. And so the other piece to this that I haven't said yet is there is a closure assumption about what sets the magnitude of that velocity of these convective structures. And that is given by work by Stevenson in 1979. And basically that closure argument just says that the velocity is basically the growth rate times the wave number of this system. Okay. It uses a very similar kind of framework to build up how those wave numbers, the superadiabaticity, and other properties of the system vary with parameters, including rotation, magnetic field, diffusion, etc. So the basic principle is that once you've done this flux maximization, this gives you what how your wave number should vary as a function of rotation and diffusion. So that's equation 15 there is the maximized one. So if you solve this polynomial for xi, which is your function, that gives you how the system varies with the various parameters. If we ignore diffusion, like I said we would, so that's setting these parameters v naught and k naught to 0, and you get a very kind of simple polynomial, fifth order polynomial, of course, which has some non-analytical solutions, so you have to do a Newton solve on this. It doesn't have rational solutions, unfortunately, that are really simple. So we just solve this thing numerically, and that gives us what the wave number is for a given Rossby number, convective Rossby number. Yes. And that convective Rossby number itself is basically the ratio of the non-rotating system's velocity to the rate of rotation, or basically 2 omega. Or omega is the rotation rate of the system.
I'm with you.
This is something that's kind of fundamental in a lot of rotating convection, both models and in reality. This basically tells you how strong the Coriolis force is relative to the inertial force in the system, which says that if you're rotating really fast, the Coriolis force will be large relative to the inertial force, and you'll have a low Rossby number. Yes. Yeah. Yep. And so this is how rotation gets incorporated into our convection model. Okay. It tells us, one, how the velocity can scale, or as you see here, epsilon is the superadiabaticity of the system. So how the temperature gradient in this Rayleigh-Bernard system changes with Rossby number. And just below there in equation 14, you can see how the velocity varies. And this is really the quantity that we care about the most, because it tells us about how the Reynolds stresses vary in the system. It tells us also how the overshooting can change. So like I mentioned in paper 1, we looked at this penetrative convection. And in that model, basically the penetration depth varies as the cube of the velocity. So that tells you how this can vary with Rossby number. Because one thing we can do is a little bit of asymptotics, which says that if the Rossby number is low enough, you can reach this asymptotic regime where xi basically scales as Rossby number to the -1/5.
Okay.
So that basically what that says is Xi increases as you decrease the Rossby number, which means that your convective scales are getting smaller and smaller.
All right.
Which also means in this case, because it's Xi to the inverse power, that your velocities are getting smaller. And so in order to maintain the same flux through the system, you basically have to, because it's a product of basically nu q of sigma, which is your growth rate, and the wave number that sigma has to increase to compensate for sigma has to decrease for the increasing Xi, your increasing wave number, which means that your velocity has to decrease.
Yes. I'm with you.
All right, so we've got this model of convection. It's very simple. It's a single mode. So this is the mode that carries the most heat in the system. It doesn't carry all of it. If you look at like a really turbulent system, you'll have a spray of modes that are actually contributing. But if you look at experiments of Rayleigh-Benard convection, it is really this mode that carries the most heat. Okay. It's about somewhere around 60% of the heat is carried by this mode.
Okay.
So it's a good approximation at first order to what the convection is doing.
Nice.
Okay, so next we look at Gravito-inertial waves. So here we have a linear system that should be given by a set of equations just below 20 there, I think.
Yeah.
It's, 21 through 25. So this is just the basic governing linearized system for Gravito-inertial waves. And basically the most important parameter there is n, which tells us how the Brunt-Väisälä frequency changes with depth. Okay. So when this is positive, then you have a stable system. And if it's negative, you have a convective system.
Yes.
And in our geometry, we've just set it to be stepwise. It's kind of the simplest thing you can do. So you're just matching two regions, one where n is large and positive, and one where you have a small Brunt-Väisälä frequency associated with the convective overturning time, which is typically much, much longer than the Brunt-Väisälä time scale, or the buoyancy time scale. Like in the sun, for instance, it's thought to be about a factor of 10 to the 5 difference between those two time scales. So the buoyancy waves are very fast with times of an hour, and the overturning time scale of convection in the sun is something like 30 days. Quite. So what we can do is just solve the system for a single variable. That gives us equation 26, which gives us the dispersion relationship for these waves, which is down just equation 28 or something like that. So it's equation 31 here is the
right. So you substitute this in.
Exactly. Yeah. So one trick here, and I can mention just a little bit there, is that there's something called the traditional approximation of rotation. And there you look at only one component of the Coriolis force, namely the radial component, in this case, the vertical component. But what you can do, and this is shown in Gerkem and Schröder 2005, is that you can make a simple substitution to remove, if you go back to equation 27, you can see there's a cross derivative term there. Right in the middle there, there's a dc dz of w term, which would make this nominally a 2D system and quite difficult to solve. But if you make a simple substitution, you can reduce this into a single variable system, really in the vertical direction, which then you can play all the typical techniques of solving Schrödinger-like equation, JWKB if you want, or you can actually just go and solve the same analytically, which is what we do down below.
Okay.
But basically all we need from this is the dispersion relationship to kind of tell us how the waves are governed by the various parameters of the system. So namely, in this case, the Brunt-Väisälä frequency, so how stiff the system is and how large, how fast the buoyancy waves are in the stable region, and then how fast it's rotating are basically our two parameters. And you can see back in equation 27 that we have this variable Xi. We'll have to jump back to figure 1, unfortunately, to kind of give you an idea of what that means.
That's okay.
But basically it tells you in which direction in a horizontal plane that the waves are propagating. So there we can see the vertical direction that is aligned with gravity. Rotation vectors off at an angle, depending upon what your latitude is in this system.
Yes.
But if you look in the horizontal plane where these modes are basically columnar, the convective modes are columnar, you'll have a plane wave of these gravito-inertial waves that are propagating along a direction xi.
Okay.
And this is the variable that we've reduced the system into. It's just that we're looking only in that direction the wave is propagating.
Okay.
It just simplifies the analysis overall.
Let's go down to 27 again.
Yeah, so if we scroll back down to where we're on equation 28,
27,
yeah, right around here.
There's
Okay, the other thing that comes into play here is that in the dispersion relationship, we have a bound on which waves can propagate in a given region. So this will change with latitude, as you see by this local wave Rossby number, that depending upon where you are in the star, you may or may not have waves that propagate. So that has to be taken into account in our analysis. Basically, there's critical latitudes above which these gravito-inertial waves cannot propagate. They become evanescent. So we have kind of two domains where things can be evanescent. You can be evanescent in radius. So for instance, gravity waves are evanescent in the convective region. But you can also have a y bound, so, or a latitudinal bound above which all of the waves are evanescent, both the gravity waves and the inertial waves.
Okay.
And that all depends upon this Rossby number.
Yeah. Yes.
Okay, so yeah, so those are our bounds. And so we look at frequencies in our analysis that are above and below those two bounded frequencies. And this kind of gives you also the hierarchy of things that are typical of stars, right? So your rotation frequency is going to be larger than the lower bound of the propagative frequencies. Your Brunt-Väisälä frequency is near the maximum possible frequency that you have because it's so much larger than the other frequencies of the system.
Okay.
That we're looking at.
Very nice.
Okay, so next we scroll down here. So what we've done here is to try to compute what the wave flux is, given one of the classical models that has become predominant in solar and stellar physics, and that is the model of Press 1981, where you look very near the interface between the convective zone and the stable zone, and you ask which waves are most likely to be excited there. And in Press's model, those waves are close to the convective frequency, not exactly the convective frequency. It can be the convective frequency, but it's close to it.
Okay.
So these are low frequency waves, which means that you're close to that omega minus bound in the system. So low frequency waves. And the idea here is to look for pressure perturbations, so changes in the isobar of the interface. So basically what's going to happen is your convection is going to give rise to pressure perturbations at that interface, which deforms it. And so these are basically deformational or interfacial excited gravito-inertial waves. And what we can do is just walk through Press's model, which starts here at equation 35, which is basically the flux in the waves. So this tells you how, given the frequency of the wave and its horizontal wave number, as well as the amplitude of the wave, so the vertical velocity there at equation 35, how much flux that wave can possess. So how much energy flux that wave can possess. And as we saw before, we have our dispersion relationship. So this relates the vertical wave number to the frequency of the wave. So these are kind of the two key components that we have in this model. And then we need to make some assumptions about how we go and compute an estimate of that wave flux, VZ. So right now that wave amplitude is arbitrary, but what we want to do is try to constrain that. And we do that with that convection model. So to do this, we basically say that the fluctuating part of the velocity field is the same order of magnitude as the convective eddy turnover velocity. So this is the convective velocity. So you match the wave velocity to the convective velocity. So that's assumption number one. So this implies that basically the pressure perturbations of the system are related to the ram pressure of the convective modes, So that's that right there.
Uh-huh.
And then assuming that the pressure is continuous across this interface, we can basically compute what the magnitude of the pressure perturbations are, which is equation 37 there.
Right.
So that's related to the magnitude of the waves and proportional to parts of the dispersion relationship. There's basically a linear relationship between P and the vertical part of the waves. So what that allows us to do is basically say that if we look at the integral of the pressure times the vertical velocity, which gives us the wave energy flux,
Yes.
if we just look at the energy equation, we can compute what f of z is, this equation 35, explicitly, under those assumptions that your eddy turnover timescale is close to the wave frequency. And if we do that, if we scroll down, we get an idea of what the flux relative of, so the vertical flux of energy relative to that of gravity waves is in figure 2 there. So basically what you see is as a function of the convective Rossby number, so how influential rotation is on the convection itself. And we can see as a function of both frequency and this Rossby number, how the flux varies. And basically the features that you see are at modest Rossby number, convective Rossby number, so those close to 1. You don't see very much change in the overall flux compared to gravity waves, which is kind of what you expect. Rotation is not playing a large role in the system, and so gravity waves are basically having the same characteristics as gravito-inertial waves. But as you rotate faster, you tend to decrease the amplitude of these interfacially excited waves. The lower you go, the less flux you have, relative flux. But actually, you also have less absolute flux as well, which you see in figure 3.
Let me ask a question here. We got we have orange lines, red lines, green lines, and blue lines. What are the lines?
So those are omega plus and minus. So the red line is omega minus, so that lower bound on the frequency.
Okay.
So this, of course, changes with latitude. And so I should say that this is taken near the equator,
okay,
where you expect maximum flux of gravito-inertial waves, and also avoids any issues with having critical latitudes.
Yes.
And the dashed green line there is the Brunnfeisel frequency. And since we're comparing gravity waves and gravito-inertial waves, you can't go above this frequency to have a meaningful comparison, because the gravity waves don't have any, or evanescent above that frequency in this model.
Okay.
And the orange line there is a critical Rossby number, which we'll discuss in just a little bit.
Okay, that's fine.
And the blue line there is a wave Rossby number of 1.
Ah, okay.
Yeah.
Okay, thank you. Over to figure 3, you wanted to go? I'm with you.
So this is the same thing except for absolute flux. It's no longer being compared to gravity waves. And so you can go above the Brunnfeisel frequency for if you're rotating fast enough. So the omega plus would basically be along this line here. Yeah. So other than that, the story is basically the same. Your absolute flux is decreasing. Relative.
Yes. Yeah. Okay.
Okay, so that kind of gives you an idea of what's happening for this interfacial model. It says that overall, as you introduce rotation into the system, you should expect less wave flux, which means that these would be harder nominally to detect at the surface even than gravity waves, which we've already heard was difficult for the sun. However, we do see these modes, so this isn't the full picture. So we need to go on to the next part of the story, which is we have not only interfacial, these pressure-driven excitations of the gravito-inertial waves, but we also have convective excitation of these modes. That's moving on to the next section there.
Okay.
And we'll come back to those figures in a bit.
Don't stress contributions?
That's it.
Okay.
So there's been some interesting work on this. So both by Goldreich and Kumar in the 90s, and then by Daniel Leakene, both in 2013 and in 2015. So basically what they do is they say, okay, we've got waves that are, for Goldreich and Kumar, it's really gravity waves and now Gravito-inertial waves, and the same for Leakene and Cottert. But what they do is they provide a way of kind of a prescription for describing how you can compute the wave flux with some fairly simple approximations to the system, kind of like what we've done above. But in this case, we know that waves are actually, gravity waves in particular, are evanescent in this convective region. So they don't see just the interface, but they see some of the convection as well.
Okay.
In terms of a source function, their tails are being wiggled by the convection, and those actually provide some excitation beyond just this pressure excitation at the interface.
Okay.
And so what we wanted to do is apply this not only to gravity waves, but to Gravito-inertial waves, in particular because inertial waves are propagative throughout the entire convection zone. So they are not evanescent there, and they can actually be excited throughout the entire volume, which gives you some hope that maybe you can have some additional excitation, much more than you would with just interfacial modes. And so this is kind of what we wanted to look at in this next section. So basically what we do here is, again, we have our linear system, as we saw before in equation 27, I think it was, or 28.
Yes.
It's not super important. It's one of those earlier equations where we describe the basic linear system.
Okay.
Yeah, equation 27. Yeah.
Just a little refresh there. Okay.
And so what we do here is we introduce a source function. So what's typically done, like in Goldreich and Kumar and Daniel Leakene's paper with Elliot Cottert, is that you have a statistical model for what the convection is doing. So like I mentioned earlier, you typically have a spray of modes in convections and nonlinear systems. You excite basically a spectrum of modes. But what we've done is we're just going to pick out the one that we think is the most important and see what its contribution is, because we know what it is analytically, right? So that means we can go and compute that source function explicitly. And that source function are basically the nonlinear terms in the Navier-Stokes equations. So these are your inertial terms, you have buoyancy forcing, if you have magnetism, you have Maxwell stresses, things like that. But here we concentrate on the one that we know is the largest, and that's the Reynolds stresses.
Okay.
It's found in Belkacem's papers, Kevin Belkacem's papers, that the buoyancy terms, the nonlinear buoyancy terms, are smaller by about a couple of orders of magnitude in stars relative to the Reynolds stresses. So that's why we're ignoring them here. So what we can do is we can apply that same framework we saw earlier that was developed in Gerkemann and Schwerer. This gives us a way of computing the normal modes of the system, which you see in equations 45 and 46.
Yes.
Those forms a complete basis on this equation, so you can go ahead and use these modes to describe any motions within the system.
Yep. And
what this allows us to do is build an equation for the amplitudes of the system, which you see in equation 47 there. So this is the full system, equations 48, 40, 47, 48. So this is the full time-dependent equation for the amplitudes. So say you start from some state where you have random noise as your initial state. This is what would evolve. But what we're interested in is the end state, right? Kind of the nonlinear saturated state. And for that, we can look at an average of this equation, assuming a large time limit, which should be up at around equation 50.
Okay, with you.
Right there. So basically what this is composed of is you average your normal modes, or you're basically projecting the source function onto your normal modes, which is the numerator of that equation. The denominator is a normalization, more or less, of that system.
Yes.
And that depends upon the Schrodinger-like potential of the system, which is that thing in parentheses there, multiplying the norm of the eigenmode.
Yes.
Yeah. Okay, so that gives us what our wave amplitudes are.
All right.
So what we need to do next is go and compute what that source function is explicitly. So we've got our model of the convective modes. So that means we can go and compute the Reynolds stresses exactly. So this is what equation 54 does. This tells you, given the chi velocity and the z velocity, so namely the velocity of the convection along the wave propagation direction,
Yes.
which is v key or chi, and then vz, which is the vertical velocity. So those are really the only two velocities in the system that we care about. So if you go and compute what those Reynolds stresses are, that is equation 54. And given the analytical forms of those two things, we can compute this explicitly. But this is where we can also tie into statistical descriptions of the system. Namely, you can think of the numerator in equation 50 as a Fourier transform, effectively, in the horizontal and time dimensions of that operator, the DTS term, the source term. And if you want to plug in something like a Kolmogorov-like description for the motions, if it were isotropic homogeneous motions, which it is not because it has gravity in the system, so it's anisotropic already, and it has rotation, so you have two anisotropies. So it kind of breaks those fundamental principles of Kolmogorov's theory. So you can't really use that here unless you want to make a very, very rough approximation, which is what we do in the paper where we talk about what happens if you look in the sphere.
Okay.
Just because applying a analytical model for the convection in the sphere is tricky. There's ways to do it. Like you could look at Boussy's models from the early noughties or other works like that, where you kind of have an analytical description for what these convective structures look like. But for now, we're sticking to this nice Cartesian picture where everything's nice and simple.
Yes.
Okay, so that gives us what the numerator is, and the denominator is known because we know what the eigenmodes are. And what we look at next is precisely how to get those eigenmodes. If we look down, I think on the next page.
Yes.
So this is where we define our system. So that's equation 57. So as I mentioned earlier, we have a Brunt-Väisälä frequency that can vary with height. And what we've chosen here is kind of the simplest possible system, where you just have a convective domain with one Brunt-Väisälä frequency, basically the convective overturning time, and then the stable region where you have a large Brunt-Väisälä frequency that's positive and gives you a stable region.
Okay.
And so you can see in equation 57, we broke it into these two regions, and you have the same equation in the two regions, just two basic different Brunt-Väisälä frequencies. In one, it's very close to zero, and in the other, it's large and positive.
Okay.
And so what we can do, we know how to solve these equations. They're very simple. It's just a one-dimensional Schrodinger equation. And so what we do down below equation 59, I think if you go look down around equation 60,
there we go.
We have our exact solution in the two regions.
Yeah, very good.
It gives us two things. It gives us what the eigenmodes look like in the two regions, how they're matched together properly at the interface.
Okay.
This also gives us a dispersion relationship, which tells us which modes actually fit in the box that we're looking at. And as we'll see later in a figure, we have a discrete set of modes, and that's because of this condition. And of course, this is a tricky one, right? It's a transcendental equation, so you can't really solve this very simply. Something you have to do numerically. But overall, the system is mostly mostly analytical. But there's a few spots like that one where you just can't do much with it, other than doing it numerically. And so we have two kind of situations here. We have one where we have something called the sub-inertial waves. So this is when you have waves that are propagative in the convection zone. And then you have super-inertial waves, which are not propagative or evanescent in the convection zone.
Okay. Mm-hmm.
That's the difference between equation 60 and 62, as well as 61 and 63.
Yes, yes.
Basically, you go from sines and cosines to
hyperbolic.
Sine H's, hyperbolic sines, and hyperbolic cosines,
Mm-hmm.
as you see in these very simple kind of traditional problems. Then as before, we can kind of look to see what we expect as the flux of these modes. So that's equation 64 there. It tells you, it relates the flux to the amplitude and the structure of the eigenmodes. So this is a local statement, so it's a flux at anywhere in the domain. And basically what we want to do is we want to say, okay, what happens if we integrate this over the stable region, so we know how much wave flux is being input from the convection zone into the stable region. So this is really an energy injection rate in a flux.
Yeah, right.
And that's, if we look up at equation 65, we can see that. So if we just plug in what we know about the amplitude of the modes, which we saw, I think, in equation 50, which is this big mess there.
That's big news.
And multiply it by the flux. It's the rest of the equation 64. So really, this big part that's just below the flux there is just the square of the amplitudes, and the rest is the rest of that equation.
Yes.
And then if we average this in z, so just integrate over the stable region, that gives us equation 66.
Okay.
And what we can do, if someone is real interested, you could go and compute what those integrals are. They are analytic and doable by hand. So that's what these next couple of equations are. They're not so informative on their own. They just go and do the integral, and that tells you tells you what they are. But if we continue down, what we can do with those is then we can make something that looks like figure 6 there. So what we can do now, because we have an analytical system, we can look as a function of Rossby number as well as stiffness. So here, the stiffness S is the ratio of the Brunt-Väisälä frequency in the stable zone to that in the convective region, or really it's a ratio of the buoyancy time scale to the convection time scale.
Okay.
So an S of 10 to the 5 is a very stiff system. So it's kind of like what we expect for the sun, where you have a large ratio of those two time scales. And what you get there is that and as I mentioned, you have these transcendental equations that you solve for which frequencies are applicable in the domain. So that's why you have a discrete spectrum here, because you only have a discrete number of modes that can be available in that system. But what you see is that relative to gravity waves, which are the flux of zero, this F0 there, the flux of the gravito-inertial waves can be larger. In fact, significantly larger if you hit these kind of resonant points.
Okay.
So there are certain rotation frequencies for which you have a large flux relative to gravity waves, even in the super-inertial regime. So when you get close to a Rossby number of 10 to the minus 0.5, something like that. So what is that, about Rossby number of 0.3, you can start to have enough flux that it's substantial. It's about a factor of 10 larger there than what you'd expect. So that's starting to be important if you want to say, well, we have this decreasing flux from interfacial waves, so that's decreasing a lot. But we have this compensating effect that because you have propagative waves in the convection zone, you can actually excite waves much more efficiently in the convection zone than you can just with pure interfacial waves. And so what that means is that as you decrease the Rossby number further, you can have even more excitation relative to gravity waves, something like up to 10 to the 10 times what the gravity waves were. So it's still less than 1 in terms of the overall flux, but the ratio is very large just because you're dealing with things that are fairly small. This is actually probably 10 to the 7. So this would say that you could still have as much flux as you do in the non-rotating system as you do in this rotating system. So you can still have a pretty important gravity wave spectrum in the system. And then basically the other plots here in figure 6 show how this changes as you decrease the stiffness of the system. So if your ratio of those two timescales, the buoyancy timescale and the convective timescale, is smaller, you have less and less of this amplification of the gravito-inertial wave flux relative to the gravity wave flux. Specifically, if you look at panel C, where you only have a ratio of 10 between those, you can decrease the flux significantly, except for in a very narrow range of Rossby numbers. And then F0 here is just how the gravity wave flux, so without rotation, varies with the stiffness, which shows that as you increase the stiffness, you expect less excitation, at least in this model.
Yes. Interesting. Okay. Nice.
Yeah, so basically, that's what we have here is that you can have extra excitation if you include that convective excitation of the modes, and it's pretty dependent upon what model you use for the convection. But what's nice here is that you can do it all analytically. This is all done just on my machine. You don't need a supercomputer to do numerical simulations of anything. You just need Mathematica. But what we can also do is we can start to say, well, now we know we can maybe place some bounds on on where you might expect gravito-inertial wave excitation. So that was back in figure 4, I believe.
Let's go back there for a minute.
Yeah, just bounce back there real quick.
Okay. Yeah.
So this shows evolutionary tracks for a range of modest mass stars, so close to solar. So you're ranging from, what is that, K dwarfs up to maybe F stars, early F stars.
Yeah.
Just from pre-main sequence up to their terminal age main sequence.
Okay. Yes.
And what's plotted on the left there is the convective Rossby number of those stars, kind of at the base of the convection zone, if I remember right. So near where we have an interface between an exterior convection zone and an interior stable region. And so what you see is that when you're very young, you're spinning very fast, and you have a very low Rossby number, which means that your ability to excite these gravito-inertial waves is much reduced, or at least the amount of flux that you might expect is much reduced compared to a later aged star. So as they progress along towards the main sequence, which you can kind of see as that peak, that first peak there. Yeah, right around there where your cursor is now. Yeah, you kind of get it's most pronounced for the more massive stars because their convection zones are so much thinner. So these curves are much more abrupt than they are for the low mass stars. But basically, what you can see is that these waves will be important for the majority of their lives, except for the more massive stars. So where their Rossby numbers basically just become too large. They've spun down, they've lost a lot of angular momentum, and so the influence of rotation is just not significant enough to expect a large gravito-inertial wave flux. Now you can still have gravity wave flux, of course, but that too is also reduced depending upon the stiffness of that interface. So that's something that you kind of have to know from the stellar model is, one, what is the stiffness, or what is the buoyancy frequency? But we also know for massive stars, more massive stars, that the convective overturning time is quite short, of the order of a day or even hours for those highest mass F-type stars, where the convection zone is very thin. Which means that stiffness might actually not be quite as large in those stars than as it is, say, for an M dwarf, for a K dwarf or a G dwarf.
Very nice.
Yeah,
it's awesome, actually. I like that shot.
Then figure 3 is or figure 5, sorry, is basically just an integral over angle, so both the propagation angle and latitude, as well as frequency. So these are non-analytical integrals, even though it is ratios are basically rational functions, but eventually you get to something where it's rational functions with sines and cosines.
Right.
It's a little bit of a mess. So you get elliptic integrals, but in any case, what you can do is you can carry out those integrals numerically for a given stiffness, and basically say, okay, what happens as you approach a large ratio of the breakup frequency of the star? Is that, as we saw in figures 2 and 3, that basically the faster you rotate, the less flux you get, except in this case, there's that critical frequency right there. Because these are not analytical integrals, we don't exactly know where that's coming from. There's some sort of weird resonance there, but it's of order a tenth of the breakup frequency, or as you see, 0.9, 9% of the breakup frequency. But basically the story is flux decreases the faster you rotate.
Away from this resonance. Interesting.
Yeah, for that interfacial minimum. Okay, so I think we've covered all the figures there. And so what we're doing now, so we've got this first kind of go at an analytical model for what we expect for the excitation of gravito-inertial waves for this simple model. And the next thing that we want to do is, of course, add magnetism into the picture, which there's been some authors who've already looked at this, like the so-called magnetic greenhouse effect, where you can have trapping of certain modes, which would lead to a suppressed amplitude at the surface of certain modes, like the dipole mode in red giants, for instance. It's one possibility. But the other thing we want to look at are more sophisticated models. Oh, my camera's not working here.
Yeah, got into a frozen flux state there.
Yeah, let's, oh, is it even gonna start now? Oh, it's not even starting now, lovely.
All right. Well, timing was fantastic then. At least we got it through.
Sorry about that.
That's okay. Just talk. So,
Yeah.
where are we heading over the next, let's say, 5 years or so?
Yeah, so we're doing a couple of different things. So one, we're changing the model that we're using for the convection. So one, like I mentioned, is to look at spherical models of this, where you have an analytical prescription for what the convection looks like in a sphere. So for this, you can look at papers by Bussy and company from I think 2002 is one paper where you have this kind of simple description of what are called banana cells, which are something that you see in 3D simulations of stellar convection. So that can give you an idea of how these nonlinear structures can influence the gravity wave excitation. And again, we're also looking at local models, but instead using self-similar flow structures, so plumes.
Okay.
So one thing that we've been working on is building a analytical model for a rotating plume, which so far has been pretty challenging. Finding the right set of equations that allows you to apply the principles of a self-similar analysis have been a little harrowing.
Mm-hmm.
Basically end up with a Lie algebra problem, and it's a little tricky. But this is building on work by Charlie Pinson from his PhD back in 2016, where basically he looked at a local model where you introduce a stochastic set of plumes, with something like 4,000 plumes being representing all the interstices of kind of supergranulation on the sun. So basically what you have are the supergranules, they're vecting around, but where they meet, you can have vortices form, and those vortices might plunge deep into the interior. And this is trying to model what happens as you have those plumes falling through the convection zone and interacting with the stable layer to give you a different way of calculating how much flux you might have at a given latitude for the gravity waves in particular. But we've also done this for gravito-inertial waves, and also included density stratification. So you just add in additional effects and more parameters into the system to see how all these things vary, which give you an idea of how you might, one, change diffusion models in stellar evolution codes, so how mixing occurs at certain boundaries. But more importantly, one thing that is really not well understood are non-local models of transport. So for instance, if you excite waves, right, they're going to propagate some distance and then dissipate away from their propagation region.
Right.
They'll deposit energy and momentum deep in the interior of the star. And so that can carry things like angular momentum, for instance, which will affect the angular momentum evolution of stars and its chemical evolution, because those things can propagate chemicals as well. And so understanding exactly what the amplitude of those waves is in those stable regions is quite an important problem, and one that's pretty unsolved yet. And there's a lot of virgin territory to go poking around with these fun analytical models. Yeah, so that's kind of where we're headed. We also have some collaborations with people who are using Kepler data, where we're trying to apply these models and see, is there some observational signatures of these kind of transitions between subinertial modes and superinertial modes, where can you actually get a handle on how do you actually see this reduction in flux relative to gravity waves or not. So we have some ways of trying to observationally test these models, and so we're working with a couple of groups on doing that in the coming year.
Yep. All right. I look forward to seeing those works over the next year or two or three. It'll be pretty cool. All right, everyone, that'll do. Thank you very much. I hope this made your astronomy day just a little bit better. And thank you, Kyle, again, for walking through your very lovely paper. And we'll see you on the next one. Bye-bye.
Thanks, Frank. See you guys.
Bye.